After our analysis of this Gram-Schmidt orthogonalization procedure, and also after finding the relationship between the length of the vector and the signal energy, we also solved few problems based on that. Now, let's move on to the next topic, that is conversion of a continuous AWGN, additive white Gaussian noise channel, into a vector channel. So how to convert this channel, the channel between the transmitter and receiver? If you remember, recall that what in an AWGN channel model of a transmission and reception system, how did we write it? We just considered the transmitted signal Si of t. This will be the transmitted signal, right? The received signal, we considered it as x of t. This is the received signal, and the channel should have what? Additive white Gaussian noise. So the white noise or white Gaussian noise should be added to the channel. This was the model which we considered. This should be additive in nature. That's why we used to call this as AWGN channel. To the transmitted signal Si of t, this is what we considered as the transmitted signal. When white noise gets added and you receive a signal x of t, this x of t would be represented as Si of t plus W of t. And that's the reason that this channel is known by the name AWGN channel, additive white Gaussian noise channel, or additive white Gaussian noise channel model, which we call. And this is the standard representation which we use in almost all our communication systems. Okay. But once you go to wireless communications in your 8th sem and all, you'll see that this channel model will always not have additive noise, but it will have multiplicative noise also, which we call them, then we call them as fading channels. So the channel will experience noise which is multiplicative in nature. It gets multiplied with the input signal, and it may cause lots of fading of the original signal. The signal may be completely faded out to zero, or it may be received in a very reduced magnitude. But all that effect we'll see most often in wireless channels. Here, even if we are considering wireless transmission channels also, we normally consider the effect of additive noise. So the major source of noise in channels is the additive white noise. Remember, white noise has uniform power spectral density. We all know the power spectral density of white noise. PW or what? What is the value of the power spectral density? It is N0 by 2 at all frequencies. So the power spectral density of white noise will have the value N0 by 2 at all frequencies. And because it is uniform throughout, we call it, we consider it to be more useful in all our analysis. Ideally speaking, it is not uniform like this, but it is in the shape of a bell curve, a Gaussian curve. Remember, this white noise is in the shape of a Gaussian or bell-shaped curve, right? It is in the shape of a bell, but the frequencies of interest to us, the frequencies of interest, that is, let me say FL and FH. Okay, this is the RF range which we are considering, the range in which we are trying to transmit and receive signals. You see in this range, the power spectral density is almost uniform. So a practical white noise curve looks to be something like this. It will actually be Gaussian in shape, but since in our area of interest, in the region where we are transmitting and receiving, we have this power spectral density almost constant and equal to the value of N0 by 2. We will consider this case, the ideal case in almost all our transmission and transmission models. So whenever we consider a channel model which is affected with white noise, we always treat this white noise to be additive, and though it is a Gaussian shaped noise, it will remain uniform in the range of frequencies of interest to us. So whatever are the range of frequencies of interest to us, in that range it will remain constant or uniform, the power spectral density. Hence, we consider a constant power spectral density at all frequencies whenever we consider this white noise. Please remember that. Okay. So this is the channel model which we have considered in our analysis. So let us consider how to convert this to a let's consider what are the input signals in this model and how to convert this into a vector channel. Okay. So we know that the input signals, what did we consider as input signals, are a set of real valued signals, are a set of real valued energy signals, if you want, you can say real valued energy signals. Let's say Si of t, we wrote it as S1, S2, S3, so on. Okay, till Sm of t. And each of these will be of duration. What? Each of duration capital T seconds. The time period of each signal we always consider as capital T seconds. And are represented, remember the representations which we considered, represented by the equation. How do I represent Si of t? In terms of its coefficients. Remember, we used to call the coefficients of the signals as Sij, and these coefficients should be multiplied with the orthonormal basis functions phi j of t for j ranging from 1 to n. So this is how we used to define each of the signals. So each of the finite energy real valued signal Si of t, say S1 of t was defined as summation S1j phi j of t, right? This is how we used to define. And what is the value of t here? T would range from 0 to capital T, one time period, right? And what would be the value of I here? I represents, I can take the value 1, 2, so on till m. Remember, I can take the value 1, 2, 3, so on till m. Okay. J we have already written here, so I need not write exclusively. J takes the value from 1 to n. So this is how we represent the input signals, which are simple finite energy signals which exist in the range 0 to t seconds. The time period of this input signal is from 0 to t seconds. And these are the signals which actually get transmitted into the channel. Okay, where Sij are the coefficients. How can I find the coefficients? Where Sij represents the coefficients, even this we have written, which can be determined. So how do I isolate Sij from this? Remember, we wrote this analysis and synthesis equation blocks also. Equations and blocks. So Sij could be written as integral Si of t phi j of t dt over the interval 0 to capital T, right? I would find the coefficients Sij using the integration of the given signal with the orthonormal basis function over a time interval 0 to t, one time period. Here you remember what is the range of I? I ranges from 1 to m because I have I. J ranges from 1 to n. This is how I represent the coefficients. Yes or no? We call one as the synthesis function. So which is the synthesis and which is the analysis function? Getting Si using the coefficients, this is called the synthesis equation, and in the block diagram this will be represented using a synthesizer. Remember, we had written this. We can write it again here anyway we need it. This is called the analysis equation, and in the block diagram representation an analyzer is used to represent equation 2. Okay, let us write that and see. Therefore, the block diagrammatic representation, we had already written this, but I need it in the beginning of this part also, because only then if I write the actual input, I'll be able to convert it into a vector channel. Block diagrammatic representation of the equations 1 and 2 are as follows. So can you write the synthesizer block diagram? For the synthesizer, I'll be using the coefficients. Si1 gets multiplied with phi1 of t and it gets added in a final adder. Similarly, Si2 gets multiplied with phi2 of t and it gets added. So on, I have what? SIM or Sij, no? J is 1 to n. So SIN it will be. So SIN gets, gets multiplied with phi n, the orthonormal basis function phi n of t, and it appears in the final adder. So this combination signal would be Si of t. See, Si is the, I is the first, what do you say? The first, what do we call this? Suffix, sorry, I'm not getting the name. Okay, you can see Si1, Si2, Sin. I is the first letter or the first thing in each of these signals. All these are finite energy coefficients or finite energy signals. So they combine to represent Si of t, and this is given by the first equation which we have written. We can see Si of t is the summation of Sij into phi j. Here j is varying from 1 to n. So you see we are multiplying each of these S values with phi 1, phi 2, phi n, and we are adding up to generate this. So this is the synthesizer. Now at the receiver, I have to consider, say, Si of t is received. I'm assuming Si of t is received, but actually what is received will be what? X of t. Remember, we showed here, when this transmitted signal passes through channel, Si of t gets added with W of t, and you don't receive just Si of t, you receive Si of t plus W of t, which we considered as the received signal X of t. Okay, so please remember, actually here, after the channel, here this is the channel with white noise. So what you receive here would actually be Si plus W. Okay, please remember this. But here I'm just considering when I receive Si of t correctly, say for example without this noise. We'll say after noise also what happens we'll show. If I receive without this noise, the equation 2 represents the analyzer part, where I can separate this finite energy signal into its coefficients Sij. How do we do it? We should multiply each time the received signal Si of t with different values of the orthonormal basis functions, and then integrate this product between 0 to t. If you remember, we called each of them as what? So you multiply this with phi 1 and then you integrate it in the range 0 to t. This product Si of t into phi 1, you integrate it. The result what you get will be S1j. It should be S1j. Similarly, or Sij, or what did we call this as? Si1. Sorry, I should get back this signal. Remember, I transmitted the signal Si1. I should get it back when I do this. Again, when I multiplied this Si of t with phi 2 of t and I integrated in the range 0 to t, I should get back the second signal Si2. Likewise, when I multiply this with phi n of t and integrate in the range between 0 to t, you should be getting the signal Sin. So this is called the analyzer, where we should get back the signals Si1, Si2 from the received signal Si of t. Assuming that the received signal is Si of t, how do I get back the signals Si1, Si2 which we had transmitted initially? Is by multiplying them with the orthonormal basis functions and then integrating. What did we call this as? You remember what was this called as? Each of this was called as a correlator. And here I have a bank of n correlators. A bank of n correlators are there in this. Every multiplier followed with an integrator is called a correlator. It's also called as product integrator. Correlator or product integrator. Remember this. Okay. So this synthesis and analysis functions we had written, and the effect of an AWGN channel will be to get a random signal X of t instead of the actual signal Si of t that was transmitted. And what would be the value of this X of t? It would be the transmitted signal plus white noise. So let's consider that and let's see what would be the output of this correlators. So you say in the actual case, W of t gets added to Si of t in the channel. Therefore, the actual received signal is, let me consider it as x of t, which is si of t plus w of t. Okay. Remember, this is the actual received signal which we have rather than just si of t. We will not directly get si of t, but we will get this signal. And remember here what the signals will exist between 0 to capital T, and the value will I range from 1 to m. I have only I here. If you have j ranges from 1 to n. Okay. And also the signal W of t, the white noise, has 0 mean. Remember the mean of white noise. What is mean? The first moment of white noise is known as the mean, and its mean is 0. For white noise, the mean of the signal is always 0. Let's say mu W is 0, and the power spectral density or variance, the second mean, is called as, these are different names of the same signal. I can call it as power spectral density, I can call it as variance, or I can say it is the second moment. Rather than second mean, I'll say the second moment. Is n0 by 2. Remember, I had showed this to you in the beginning itself. For white noise, the power spectral density remains n0 by 2, and it is considered constant in all the frequencies of our interest. Okay. So how do I write this? Variance, we write it like this, right? So variance is sigma square, which will be, for white noise, it will be n0 by 2. For all values of j ranging from 1 to n. If I call it as Wj, for all values, it will be n0 by 2, remember. Okay. Therefore, now we can find the actual output of the correlators or product integrators in the above, let's say in the above representation, as say x1, x2, x3, so on. Okay. For each of these values, what we are calling as SI1, instead of SI1, I'll be receiving x1 here. Here I'll receive x2. And remember, that is when we consider x of t as the actual input, which would be sum of the transmitted signal and white noise. Okay. So when we say there is noise added, so the received signal would be x1 instead of, okay, SI1. And here I'll say I'm receiving x2 instead of SI2. Here I'm receiving xn instead of SIN. That's what is the actual received signal when white noise is present. It would be SI1, SI2 for the ideal case when there is no white noise. So I'm calling these signals as x1, x2 till xn. Okay. Now, let's say output of the jth correlator is xj. So if I consider the output of the first correlator, it is x1. Second correlator, it is x2. Output of the jth correlator will be xj. Okay. Just a simple representation what I'm using. Therefore, this xj is nothing but the sample value of the random variable. Can I write it as RV of the random variable? Whenever I write capital RV, please understand it is random variable xj. So xj is the actual random variable, okay, which is defined, and small xj represents a sample of this capital Xj. So capital Xj is the random variable and small xj would be a sample value of this random variable. So which is defined for each product integrator or correlator as follows. How do I define this xj value? In this case, for each of this, the output xj, what could I define it as? You see, it is the product of the received random variable x of t, or if I say x of t is the complete random variable, small x of t will be a sample of this. Remember, we usually consider samples. So I can say this small x of t into phi j of t integrated between 0 to capital T dt. That's how we have represented. So how do I write each of these x values, x1, x2, so on? That's what we are trying to write here. Therefore, this small xj can be written as integral the input signal x of t into phi j of t integrated between 0 to t dt, right? So x of t is the actual input. It's a sample of the random variable capital X of t that gets multiplied with the corresponding orthonormal basis function phi j of t, and then the product is integrated between 0 to capital T to help me get the values x1, x2, so on till xn. Xj can be obtained like this. So what can I write this as? What is this x of t? Remember, we know x of t is nothing but the transmitted signal Si of t plus the white noise. Yes or no? X of t can be written as the transmitted signal plus the white noise in the channel. White noise which gets added in the channel. We have already written this so many times before. This into phi j of t dt, or I can write this as integral 0 to t Si of t phi j of t dt plus integral 0 to t w of t phi j of t dt. Can I write it like this? I am just splitting. See, this signal x of t, which is the received signal, was the transmitted signal plus white noise. Now I am just splitting and multiplying in this. Do you remember what is this? Si into phi j? We wrote in the beginning only. What is Si into phi j? See here. It is your analysis equation which represents the coefficients Sij. Sij is given as integral Si into phi j. The same thing I have got here. So can I write this as Sij plus this whole thing? I will just give it a name, Wj. Let me call this as Wj, where Wj represents the product of white noise with the orthonormal function phi j of t integrated over the time 0 to t. Okay. let me call, what did I call this? This was the expression for xj, which is the output of a correlator. Therefore, output of the jth correlator xj can be defined with this equation. I lost count of numbers. Okay, we have 3 here. Let me call this equation 4. Okay, so this is the actual output of the jth correlator. So instead of getting Sij here, or say for example, I'll consider the second correlator. In the second correlator, I have to multiply Si of t with phi 2 to get Si2. But I'm not receiving Si directly. I'm receiving another random variable x of t, whose sample value is small x. So this is the random signal x of t which is received. When that gets multiplied with the orthonormal basis function phi 2 and integrated in this range, I'm supposed to get x2 and not si2. We'll see what is the difference between these two, whether si2 and x2 will be equal or whether they will be different, and if they are different, how different they are, we will try to see. Okay, so actually this is the vector notation and this is the signal notation. I hope you don't have any doubts with this. So what is WJ and what is Sij? We already know that. Now let's say the noise process, W of t is 0 mean and with power spectral density or variance n naught by 2, right? We know that. Therefore, the correlator outputs also have zero mean values Sij and the PSD or variance n naught by 2 for Wj or W of t, we'll say. Let's consider. So to show this, let us consider a new stochastic process. It will be random only. New stochastic random process x dash of t, whose sample function. So this I'll take whenever I consider a process or a random variable, I should take capital, and its sample function will be small x dash of t. See, capital X of t was the random variable or the random process. Small x of t was its sample function. That's how we treat it. So now what we are doing to find what is the end result after the analyzer, let's consider a new random process x dash of t, which has a sample function small x dash of t, which is related to the received signal, as follows. So let me just consider a new signal which is related to the received signal as shown below. I'll say x dash of t should be, this is the received signal x of t, from which I'm going to subtract just the summation of the product of this received signal xj with the orthonormal basis function phi j. So what happens if I consider a new signal which is having this kind of relationship with the received signal? Let me call this equation 5. This is just a consideration which will give us the correct end result or the relationship. Okay. So using this, let's say substituting the value of x of t as si of t plus w of t, and we know what was xj. This x of t was the received signal which was transmitted signal plus white noise. And what did we consider as this xj? We showed that this xj, okay, which is what? The jth correlator output. Xj is the output of the jth correlator. It is the sum of Sij plus Wj. We have shown this in equation 4. Xj is the coefficient Sij plus a noise process Wj. In equation 5, what do I get? I get x dash of t is Si of t plus W of t, the first function. In place of x of t I am putting. Then here I have j is equal to 1 to n. For xj I am going to put Sij plus Wj into phi j of t. We already have shown all this. So if I substitute and if I simplify next, what do I get? This is Si of t plus W of t minus, here j is equal to 1 to n Sij into phi j of t plus summation j is equal to 1 to n Wj into phi j of t. What is this value? Sij into phi j. That was your synthesis equation, yes or no? Do you remember the first equation which we wrote? Sij into phi j, summation for j is equal to 1 to n. It's your synthesis equation here. What is the value of this function? This we'll keep it as it is, W of t minus, this is nothing but Si of t, and this function I'll just keep it as it is unless I give it some other name, Wj into phi j of t. So here if I simplify, can I cancel this Si and this Si? So what is it which remains? We have x dash of t, the new function, is directly related to the white noise minus, this is minus into plus, minus summation of the noise process into the orthonormal basis function for each of the correlators. So in each correlator, we are going to take this part of the white noise. What is Wj? I hope you remember. Wj is nothing but integral of the product of the white noise into phi j. See, in each of these cases, this white noise also passes through this multiplier. So I will have, just like how we'll have the signal into phi 1, I will have white noise into phi 1, white noise into phi 2. And then when I integrate this, you will have integral of white noise into the orthonormal basis function. That's what we called as Wj, right? That for each correlator, the part of the white noise which changes would be in this form, Wj. Now, the actual signal x dash of t, what we have considered, can simply be the difference between the input white noise and the white noise which we have after it is multiplied with each of the what? orthonormal basis function, summation of all this. So summation of the part of the white noise in each of these functions, each of these products and this. So which part of the white noise when it gets multiplied with this? So the actual white noise minus the processed white noise in these correlators. So I can call this as, let's say, let me call this as W dash of t, W dash of t. Hence, what is the equation number? 6. Hence, this shows that the sample function x dash of t, which we had considered, depends only on the channel noise W of t. It depends mainly on the channel noise and not the signal. So we have considered the function x dash of t. And what did we consider that function as? X of t minus something. That something we represented as the noise due to the actual white noise passing through the correlators. This is the processed noise in the correlators and the actual received signal is x of t. Finally, this equation ended up as the difference between the actual white noise and the processed white noise. Or I can say this x dash of t mainly depends on channel noise and it's almost independent of the signal. I don't even have the signal term here. Si of t got cancelled with Si of t and this x dash of t is just depending on the white noise. Okay. Therefore, now on the basis of the initial equation, which equation had we taken? Say we had considered x dash of t as x of t minus what? Summation j is equal to 1 to n xj into phi j of t. This was what we had considered x dash of t as. Let's substitute that. X of t, let's find. Then x of t can be written as x dash of t plus summation j is equal to 1 to n. All these are just manipulations to get the equation in a different form. To find what is actual x of t, it is the assumed signal x dash of t plus this value. Okay, we proved this value. This is, what was x dash of t equal to? We showed x dash of t is nothing but w dash of t. And what is w dash of t? W of t minus summation wj into phi j. And what is wj? Integral w of t phi j of t in the range 0 to t. Please remember each of this. So I can replace x dash of t with w dash of t plus summation j is equal to 1 to n xj into phi j of t, right? Or I can just say x of t is the summation j is equal to 1 to n. I'll write this term in the beginning. Xj into phi j of t, this gives us the analysis function. Okay? Plus w dash of t. So this would be the representation. We have drawn this in the analyzer. Remember, the analyzer includes what? Product of the received signal x of t with the orthonormal basis function phi j of t and that integrated in the range 0 to t. That's what we have considered in our final equation, and summation of all that plus the summation of the processed white noise. W dash of t, which is given by this equation, W of t minus summation Wj into phi j. This is processed white noise in the correlators or in the bank of correlators. If you want, you write here. Represents the processed white noise in the bank of n correlators or product integrators. So I can write the received signal as a sum of that processed white noise and a sum of the actual signal. Okay. So this is known as the conversion of a given AWGN process to a vector channel. We have represented it using vectors xj, phi j. See, xj, phi j are the vectors. Okay. If you want, you can directly write phi j here. Usually, though we consider the orthonormal basis function as a function of time. So here, all what we are doing is, I think the next is I have to characterize the correlator output. So before doing this characterization of correlator, it will need more time. Let me just brief up this. By the time you can enter your USNs, Srishail has already started. Okay. So all of you drop in your USNs. Let me just brief this once. So what we are doing here is we are trying to represent this continuous AWGN channel into a vector channel where we have considered vectors as inputs. Here SI1, SI2, SIN are all vectors if you remember. And Si of t is the continuous finite energy signals. Similarly, transmitting these vectors, signal vectors Si1, Si2, Sin through the channel involves multiplication of each vector with an orthonormal basis function and addition of each of these products to generate the finite energy signal Si of t. This is how we design a transmitter. See, when you actually do ASK, FSK and all, you have done it in the lab. I think you should understand what this truly means. So each signal here will be in the form of a sine or cosine, or the orthonormal basis function will be a sine or cosine. This signal will be 1 or 0, which can be represented by some bit energy EB. So that signal gets multiplied with a sine or cosine and it gets added to the next signal. If one is multiplied with a sine, the other will be a cosine. They are orthonormal signals. Sines and cosines are orthonormal. So it gets multiplied by those signals and then it is added to be sent on the final channel. Okay. So please remember that. That's how it is done. And all these are vectors now. They are multiplied with the orthonormal basis function to generate the continuous finite energy signal Si of t. On the channel, we have white noise added to the signal. So Si of t plus W of t becomes a random process or a random variable, capital X of t. And we'll take a sample of that random variable, small x of t. And we'll try to do the analysis part to get back the original vectors Si1 to Sin. And what is there in the analysis part? You should take the received signal, multiply it with the orthonormal basis functions again, the reverse process. And after multiplication, you should send it through a low pass filter, which is nothing but an integrator. Multiply and low pass filter or multiply and integrate. Please remember, integrators are the best low pass filters. Try to understand what all this means practically, only then it's easy for you to remember and recover. Okay. So you multiply, here you're just multiplying each vector with a sine or cosine, some basis function, and you're adding and transmitting. Here you will do the reverse process. Again, the received signal will be multiplied with the sine or cosine, and then you will low pass filter. Remember, multiplication usually generates many products, and part of it will be the noise also. And when we low pass filter, we should be able to get back the original signal. That's your analysis. And the same thing we are trying to prove by writing this in the form of a vector notation. So whatever equations we get, Si of t, the synthesis function, Sij, the analysis function, the block diagram, and then we'll be writing xj as the random variable for one of the correlators here. Remember, each one, every branch is a correlator, and this is a bank of n correlators which we have. For one of the correlators, when I consider the random variable as capital Xj, its sample function will be small xj, which is the output of the correlator. The output of this correlator will be this received signal x of t, right? X of t here you have into phi j of t integrated between 0 to t dt. This is how we represent the output of one correlator xj, x2, x1, whatever it can be. So we'll consider that representation, and we were able to show that xj could also be represented as a vector Sij plus wj. And later on, what we did, we wanted to show what would be whether the final output could be written in terms of signal plus noise. So we considered a new random signal x dash of t, which was defined as the received signal minus some value. Okay. And that value we tried to simplify by substituting for the received signal and this xj. And finally, we were able to show that the assumed signal was nothing but directly dependent only on noise and not dependent on the signal. So you have assumed a signal which depends just on the white noise and the processed white noise in the bank of correlators. This we call as W dash of t. Hence, it shows that x dash of t depends on this. And finally, we were able to show x of t, the received signal, can be written as the sum of the summation of each of the signal in each of the correlators plus the noise. If we are able to